This conference will now be recorded.
Good evening, ma'am.
Good evening. Today we'll start with uses of phosphorus trichloride, how we can make phosphorus trichloride, that is PCl3, and what are its chemical properties that we have already seen in last class. Now we will see its application. After that, there will be another important compound of phosphorus, halogen related compound, which is phosphorus pentachloride, that is 5 chlorine atoms will be present. After that, there will be discussion related to oxoacids of phosphorus, and then another group, that is the next group, group 16, will be started. Uses of phosphorus trichloride. Main use for this compound, that is PCl3, is to make phosphorus oxychloride. Now phosphorus oxychloride is POCl3. Okay, so you can understand that from PCl3 you are making POCl3. So this is basically oxidation reaction. So obviously we will use some oxidizing agent. Either you can use oxidizing agent, or you can also use some that is oxygen directly. So in the first equation you can see we are using oxygen directly, you are getting POCl3. In the second case we are using potassium chloride, KClO3, which is basically oxidizing agent. In both cases we are getting phosphorus oxychloride. It is used as important intermediate in the production of phosphate ester insecticides. Okay, so when we synthesize any phosphate ester insecticides, then this compound is basically intermediate. That is, it is generated, then from it the final compound will be generated. It is also chlorinating agent that we have already seen in its chemical properties. That is, if you take alcohol or carboxylic acid, then in presence of PCl3, OH group of alcohol, that will be converted to Cl, and OH group of carboxylic acid, that will also be converted to C. So alkyl alcohols converted to alkyl chlorides, carboxylic acid, that will be converted to acid chloride. And it also has sometimes used as catalyst. It is used in the production of phosphorus pentachloride, that we are going to see in the next slide, that is PCl5. Then also thiophosphoryl chloride, pseudohalogen, and phosphonic acid. So these are some phosphorus related compounds for the production of which we can use the starting material, that is as starting material we can use phosphorus trichloride, that is PCl3. Next compound is phosphorus pentachloride. So this is the appearance, white solid, and it has trigonal bipyramidal structure. See, 3 chlorine atom attached to phosphorus, and these 3 chlorine atoms, their position is equatorial. It is pentacoordinated, and 2 chlorine atoms that are present in the axial mode. So it has TBP geometry, trigonal bipyramidal. This is a trigonal, and these two, that is, if you consider the upper part and lower part, there will be 2 pyramids. So that is why the name is trigonal bipyramidal. How you can make it? We have just seen the application of PCl3 in the previous slide. That is, we can use PCl3 for production of PCl5. So here you can now see the reaction. PCl3 reaction with dry chlorine, excess dry chlorine, and we are getting PCl5. We can also use SO2Cl2 directly on phosphorus, that is P4, because this is the reagent which is chlorinating reagent, that is, it provides chlorine atom. So directly from phosphorus you can get PCl5 by using SO2Cl2. Now some points related to its structure. When it is in gaseous phase or liquid phase, then it will have this type of trigonal bipyramidal structure, that is TBP. The structure that is already shown here. Here 3 equatorial PCl bonds are equivalent, and the angle between them is 120 degree. Now the 2 axial bonds, that is 2 axial PCl bonds, that are longer than the equatorial bonds. So in the equatorial position you have 3 PCl bond, and in axial position you have 2 PCl bond. Now the axial position, the PCl bond that you have, that is actually longer than the PCl bond that is present in the equatorial. Now, what is the reason behind that? Because this chlorine atom that is present in axial position and also the lower chlorine atom, this chlorine atom, it is 90 degree from this 3 chlorine atom, because the angle between these 2 chlorine atom is 90 degree. That means there will be bond pair, electron repulsion. Similarly, this chlorine atom is also having 3 chlorine atom at 90 degree. So it will also face bond pair repulsion. So to avoid that repulsion, this distance between Cl and P, that will increase. But if you consider any equatorial chlorine, it has 2 chlorine atom at 90 degree position and 2 chlorine atom at 180 degree from it. That means here comparatively chlorine atoms, that is surrounding chlorine atoms, they are far from it. So that is why here bond lengths are not so longer, but axial bonds are longer. So axial bond pairs suffer more repulsion as compared to equatorial bond pair. Fine. So this is the structure in gaseous phase or liquid phase. But when it is in solid state, now it exists as this type of cation and anion. So see here, if we count the total number of P and Cl, it is basically P2 Cl 10. That is 2 into PCl5. But in the cationic part, you have 1 Cl less. In the anionic part, you have 1 Cl extra. That is why it is positive and negative, because 1 chlorine you have removed from 1 PCl5 unit, and that extra Cl minus is added to another PCl5. So that is why it is anion, PCl6 minus. So PCl4 plus, it is tetra coordinated because 4 chlorine atoms attached, and the anionic part 6 chloride ions are attached. Okay, so here coordination is 6. So the first portion, that is actually tetrahedral, and the second portion, that is the anionic part, that is having geometry octet. So see, this is the structure, but remember this type of structure you can get only in solid state, because in solid state, if you see carefully, it is positive charge and negative charge. That means there is some ionic interaction between the cation and the anion. Okay, an ionic interaction that is present in ionic solid. So that is why this type of cation anion present, but it is not present in gaseous or liquid. So this part is tetrahedral, this part is octahedral. Okay. Its physical properties: there is pungent odor, unpleasant, yellowish white solid, and it is soluble in carbon disulfide and benzene. Now both these compounds are basically we consider it as organic solvent. Okay, so it is soluble in organic solvent, and that is the reason PCl5, it can also be used for as chlorinating agent for alcohols or carboxylic acid, and alcohols and carboxylic acid, they are from organic chemistry. Now alcohols and carboxylic acid, as they are soluble in this type of organic solvent, and PCl5 is also soluble in this organic solvent, that means it can easily be used as reagent. Okay, so any doubt in this slide?
No, ma'am.
Chemical properties: if you are heating PCl5, then there will be decomposition, and it will be decomposed to PCl3 and chlorine gas. See, this is actually the reverse reaction. When you have prepared PCl5, you have taken PCl3 and chlorine together and you are getting PCl5, but now you are heating it and you are getting the original starting materials, PCl3 and chlorine. When it reacts with water, that is hydrolysis, first you are getting phosphorus oxychloride, that is POCl3, but this is partial hydrolysis. This is not complete hydrolysis. So why it is important to know individually these two reactions? Because if the question is such that what is the product of partial hydrolysis, then your answer will be POCl3. But if it is what is the product of complete hydrolysis, then it will be different product. So that is why, see here we have two reactions. When it is reacting with water first, there is formation of POCl3, but when it is complete, now the final product is H3PO4. Okay, so different types of that is partial hydrolysis or complete hydrolysis, depending on that we are getting different products. Reaction with metal. Here we have taken silver as metal and metal is converted to AgCl. So from metallic silver we are getting silver chloride, and PCl5 itself is converted to PCl3. Another metal taken, which is tin. Tin is also converted to the corresponding chloride, and PCl5 is converted to PCl3. Now the formula is different, and it has to be because silver can have oxidation state +1, but tin can have +4. So depending on the oxidation state of the metal, different oxidation state. So that is why the formula is also different. And this is that is the next reaction that you are seeing here. This type of reaction you have already seen in case of PCl3. In last class also we have seen how when you take any alcohol like ROH, in presence of PCl3 it is converted to RCl. Similarly, if you have taken any carboxylic acid, it is converted to RCOCl, that means acid chloride. So same reaction we are also seeing here, but now instead of PCl3 you have taken PCl5, but the reaction pattern is same. That is, in each case you are getting the corresponding alkyl chloride, or it may be acid chloride, depending on you have taken alcohol or carboxylic acid respectively. Fine. And in each case PCl5 itself is converted to POCl3. So this is also important. You can consider this reaction as if application of PCl5. It can be used as chlorinating agent in organic chemistry. Okay. So now we will see the application. Used as chlorinating agent, so the last reaction that you have seen. Then used as catalyst in the manufacture of acetyl cellulose, the plastic film on which motion pictures are printed. So these are industrial application. Then or chlorinating agent in organic chemistry, and it's useful for replacing hydroxyl group by chlorine. That is, if it is alcohol, then also OH group is substituted by Cl, and if it is RCOOH, then also this OH part is converted to Cl. So basically it is conversion of hydroxyl group by chlorine. In pharmaceutical industry, it is used in the manufacture of penicillin and cephalosporin, used to produce acid chloride, that is RCOCl, and cyclization, condensation, this type of reaction, this molecule can be used as catalyst. We have a problem here. The number of non-ionizable hydrogen atoms present in the final product obtained from the hydrolysis of PCl5. Remember, there are two types of hydrolysis possible. When it is partial hydrolysis, the product is POCl3. But when it is complete hydrolysis, the product is H3PO4. In this question, it is asking the final product obtained from the hydrolysis. That means here the statement basically means the product of complete hydrolysis. But it is written in a different way. It is written that final product. That means first POCl2 will be produced, then from it H3PO3 will be produced. So it is different. So hot water hydrolysis proceed completely to orthophosphoric acid, that is H3PO4. But we have to find out what is the number of non-ionizable hydrogen. Now in this molecule, you can see there are total 3 hydrogen. Now if we draw the structure, actually it is oxoacid of phosphorus, that will be discussed separately just after this slide, where you will be getting the structure of all the possible oxoacids. Okay, now what is oxoacid? Oxoacid means there will be any central atom, suppose it is E, and double bond oxygen will be present. Now in some cases there is also presence of OH, and also some hydrogens can be present which is directly attached to E, but it may vary. But the bonds that must be present is E double bond O, this will always be present. So that is why it is called oxoacid, because this is also. Now H3PO4, its structure is like this. Here we have 3 OH. Now when hydrogen atom is attached with oxygen. As you can see, 3 hydrogen are attached with oxygen. These are actually ionizable hydrogen. So here ionizable hydrogen atom total ionizable hydrogen is equal to 3. But if there is any hydrogen which is attached directly to phosphorus like this, suppose this is the molecule, in that case you can say that this hydrogen is non-ionizable. Okay, but if it is attached to oxygen, then only it is ionizable, because there is some electronegativity difference between H and O. So after ionization, what you will get, suppose this part, if it is ionized, it will be like this, O minus, because oxygen is highly electronegative, it can carry negative charge. That is why ionization is possible, that is H plus O minus. But phosphorus is not so electronegative like oxygen. So here you cannot expect ionization like P minus H plus that you are having here. So that is why this hydrogen is not ionizable. But if you look at this molecule, that is H3PO4, you do not have any hydrogen which is directly attached to phosphorus. That means answer will be 0. Okay, because it is asking number of non-ionizable hydrogen, and non-ionizable hydrogen not present. So that is why correct answer will be option A. Okay, but if it is asking how many ionizable hydrogens are there, read the question carefully what it is actually asking for, whether it is non-ionizable hydrogen or ionizable hydrogen. So if it is ionizable, in that case the answer should be 3. But here it is non-ionizable, so that is what is 3. Okay, the question is clear. Is there any doubt? Now we will see all the oxoacids of phosphorus. In all the oxoacids of phosphorus, hybridization of phosphorus atom is sp3. So that is common thing. So if it is sp3 hybridized, that means there will be tetracoordination and tetrahedral geometry. So 4 groups will be attached to phosphorus in tetrahedral geometry. Now in this acid, there must be presence of p double bond O, because in general, if we consider the structure of oxoacid, not necessarily it has to be oxoacid of phosphorus. Suppose oxoacid of any other element, suppose oxoacid of sulfur, that you will also see in group 60. So in general, if we see, suppose instead of P, if I am writing E, that is any element, then E double bond O and E OH bond both must be present. So this acid, it must contain 1 P double bond O, 1 P OH, and if it is that is, if E is phosphorus, so then obviously it will be oxoacids of phosphorus. Now those oxoacids in which phosphorus having lower oxidation state. Now by lower oxidation state, which value we are actually trying to mean? It is the value which is less than +5. That means +3, +4, +1. They also contain either pH bond or PP bond. But remember, not both together present. So when it is oxoacid structure, you should have, that is, these 2 bonds will always be present. That is mandatory. But if the oxidation state is lesser than +5, that means +1, +3, +4, like this, in that case you will also have some pH bond or PP bond. But remember, not both together. Next, ionizable hydrogens are acidic in nature. Remember in the last question what you have seen, 2 types of hydrogen. Ionizable hydrogen means which is attached with oxygen. They are acidic in nature because it is just like, remember, it is dissociating as O minus H plus. That means it is proton type of nature. So obviously it will be acidic in nature. So if it is asked what is the value, basicity value of any oxoacid, basically the answer is the total number of ionizable hydrogen. That is actually the basicity. But if there is non-ionizable hydrogen that are not acidic in nature, they are non-acidic and they are non-ionizable, but there is another feature present that they are responsible for reducing nature. So the oxoacids of phosphorus in which there is hydrogen atom present directly attached to phosphorus, in those cases you can expect reducing nature. In the previous example in H3PO4, you have seen there is no H bond that is H atom directly attached to phosphorus. That means you cannot expect any reducing nature. Fine. Now here we have this oxoacid. We have how many hydrogen? It is H4, P2, and O4, right? Now these hydrogens are ionizable, but this hydrogen, as it is directly attached, it is non-ionizable. And as we have mentioned that when there is oxidation state lesser than +5, so in this case phosphorus oxidation state is lesser than +5 oxidation state is mentioned. Now how we will understand? See how many phosphorus oxygen bonds are there? 1, 2, 3, 4. And how many phosphorus hydrogen bonds are there? It is only 1. So for each phosphorus oxygen bond, you have to consider the oxidation state of phosphorus. It is +4. And for each pH bond, you have to consider -1. Now +4 -1 together, what value you are getting? It is +3. So that is, in this way you can understand what will be the oxidation state of phosphorus. That is, you can calculate. Okay. So this molecule is known as pyrophosphorus acid. And see here, as the oxidation state is lesser than +5. And what we have already seen that there must be presence of pH bond or PP bond. But here we do not have any PP bond, but we have pH bond. 2 pH bonds are there, right? So these are some important points that you should remember, which will help you to answer the questions related to oxoacids correctly. Some more oxoacids we will see with different oxidation state. H2PO4, sorry, it is H3PO4. H3PO4, this molecule we have already seen in the last question, and it is known as orthophosphoric acid. Here we do not have any pH bond. All the hydrogens are ionizable. So these hydrogens are in orange color. And here oxidation state of phosphorus is, see, total 5 PO bonds are there. So here oxidation state is +5. Then the next molecule, that is pyrophosphoric acid, H4P2O7. In this case, it is pyrophosphorus acid, but here it is pyrophosphoric acid. Try to understand the difference. Here we have total 4 OH. So we do not have any pH bond. No, that is, reducing capacity will not be present because pH bond is not present. Now here also oxidation state surrounding phosphorus, there are total 5 PO bond. So here also the oxidation state will be +5. Now the next molecule, see, this hydrogen is having different color because it is directly attached. So it will have some reducing property. And here oxidation state, how we will understand? Total 4 PO bond, 1 pH bond. So oxidation state is +3. Fine. And as the oxidation state is +3, so that is why you have pH bond according to this condition that is mentioned in this third point. Then H3PO2, now you have 2 H directly attached to phosphorus. Here how many PO bond? Total 3 and 2 pH bond. So +3 -2, oxidation state is +2. Then the next molecule is cyclic in nature. It is cyclotrimetaphosphoриc acid. Formula is HPO3 Now here in this structure, actually it should be like this. That is first oxygen, then H, because hydrogen is not attached to phosphorus. Oxygen is attached. Be very careful when you draw the structure. And surrounding phosphorus, there is total 5 PO bonds. So that is why here also it will be +5 oxidation state. And see, we do not have any PP bond or pH bond, right? Because oxidation state is +5. Only when it is lesser than +5, we will get some pH bond or PP bond. The next one is polymeric in nature. So that is why, because both sides, it is, the structure will be continued. And here it is polymetaphosphoric acid. This is also metaphosphoric. This is also metaphosphoric. But the difference is here both side is continued. Otherwise, see, structure is same. If you just join this both side, you will get the structure of cyclo, because it is HPO3 whole 3, but here it is HPO3 whole N. So it is cyclic structure, but it is polymeric structure. And you have total 5 PO bonds, so that is why it is also +5. and you do not have any pp bond or pH bond. So reducing nature will not be present. Now page 4 P2O6, it is hypophosphoric acid. Now we have some pp bonds, so oxidation state must be lesser than +5. So we have total 1, 2, 3, 4, total 4 PO bond, and we do not have any pH bond, but we have pp bond. Now for pp bond, as it is same element, we will not consider any oxidation state. So here oxidation state will be simply +4. So in this way, you can easily calculate oxidation state of phosphorus in each compound. And pyrophosphorus acid, this molecule you have already seen here, same molecule H4P2O5, and here we have 2 pH bond. So related to the structure, is there any doubt? Now we will see how we can make it, but before that we will see two reactions. 4H3PO3. H3PO3, just have a look, and also the next one is H3PO2. H3PO3 is this one. Here you have 1 pH bond, so you will have oxidation state +3, and it will also have some reducing nature. And in the structure H3PO2 also, oxidation state is +1, that means lesser than +5, and you have 2 pH bond. Now look at this reaction. Acids where +3 oxidation state of phosphorus is present, there is a tendency for disproportionation. Now disproportionation, this is a process in which what happens, same element will be undergoing oxidation reduction simultaneously. So H3PO3, as their oxidation state is +3, so see, it is reduced to -3 oxidation state in case of phosphine molecule. So from +3 to -3, this is actually gain of electron, so this is reduction. And in case of H3PO4, now it is having oxidation state +5, that means from +3 to +5, it is loss of electron, so this is oxidation. So same element phosphorus is undergoing oxidation reduction simultaneously, so that is why this is disproportionation reaction. So whenever the acid in +3 oxidation state, there is a tendency for disproportionation, because this oxidation state is intermediate. It can move towards more positive value, or it can move towards negative value, or any other lower value. But if it is suppose +5, then obviously disproportionation is not possible, because from +5 further oxidation is not possible. That is the maximum oxidation state. As +3 is the intermediate oxidation state, so that is why you can expect disproportionation reaction. And we know where pH bond is present, strong reducing property also present. Now in case of H3PO2, there are 2 pH bond. In the structure we have seen that. Now higher is the number of pH bond, higher will be the reducing power. And in this reaction, what reduction we are getting? AgNO3 from +1 oxidation state, silver is now converted to 0 oxidation state. So it is gain of electrons, so it is reduction. And what is the fate of phosphorus? Now from H3PO2, it is converted to H3PO4. That means from +1 oxidation state, now it is converted to +5 oxidation state. So H3PO2 itself is losing electron, and it is oxidized to another oxoacid, which is H3PO4, and silver from +1 state. Now you are getting metallic silver in 0 oxidation state. So this proves its reducing property. Now we will see how you can make different types of oxoacid. Though preparation methods from exam point of view, these are not very important, but mostly the importance are the features related to its structure, its oxidation state, in which case there is reducing property possible, in which case disproportionation possible, how many PO bonds are there, or PP bonds or POP bonds. These type of questions are very common, but not the preparation of oxoacid, but still we'll see what are the processes by which we can make different oxoacids. First, we have H3PO2. We can make it by taking phosphine and iodine we are using as oxidizing agent, because see, from here oxidation state is -3, but here it will be +1. That means it is undergoing reduction, oxidation, right? And iodine itself is reduced because it is acting as oxidizing agent, so it will gain electron. So from 0 now it is -1 iodide. Then H3PO3. Now we have taken the oxide of phosphorus P4O6 in presence of water. This is actually hydrolysis reaction because it is reaction with water. We are getting H3PO3. Another method is, if there is hydrolysis of phosphorus trichloride, then also you can get the same product. Next oxoacid H3PO4. Now in H3PO4, you have to start from this type of compound. See, calcium 5, 3-phosphate and X. What is X? X may be any halogen or it may be hydroxide group also. Now this compound of calcium and phosphate treated with water and H2SO4, and you are getting H3PO4. And this is the fate of the calcium compound. It is converted to calcium sulfate and HX. Now this may be HF, HCl, HBr or water, depending on what is the nature of X. So this is one method. And another method is, now you have taken another oxide of phosphorus, which is P4O10. Remember, it is dimer of P2O5 and bubbles H2O. That means this is also hydrolysis, and you are getting H3PO4. This is 3 oxoacid. The next 3 oxoacid, number 4, H4P2O6. Now for its preparation, we have taken phosphorus, and here first we are getting Na2H2P2O6, but this is not the final product. See, here we have 2 sodium, 2 hydrogen. If you are passing this compound through hydrogen resin, now hydrogen resin means resin is some polymeric structure compound, and hydrogen atoms are attached with resin. So 2 hydrogen retain, that means these 2 sodium atom will be replaced by 2 hydrogen. So now total number of hydrogen will be 4, and in the place of resin, now this hydrogen sodium will be there. So this is basically exchange, and you are getting H4P2O6. There is another method also, which is red phosphorus treated with NaOH, alkali. Next, oxoacid H4P2O7. You can make it starting from H3PO4. And that is 2 H3PO4, basically condensation type of reaction. One water molecule is removed. H3PO4, the structure is HP. Now, if you are writing another molecule, if you are removing water molecule, then you will get POP linkage, which is basically this H4P2O7. And the last one, this is polymeric in nature. Remember the structure HPO3 whole end. You have to simply warm H3PO4, but it is very high temperature, HP50 Kelvin, because polymeric structure you are making. So obviously, to make this last structure, we have to provide very high amount of energy. So that is why high temperature. So these are the different preparation process for these 6 oxoacids. Fine. Problem related to oxoacids, and these type of problems are actually very common. The pair that contains 2 phosphorus hydrogen bond in each of the oxoacid. So in each option you are getting 2 molecules of oxoacid, but in total how many different oxoacids are there? It is basically total 4. See, one molecule is H4P2O5, then H4P2O6, H3PO3 and H3PO2. So basically we have total 4 oxoacid, but different permutation combination they are together. Now we know what are the structures of this oxoacid, because if we want to know what is the oxide, whether there is pH1 present or not, then you should know the structure, right? And another way also you can do that, you can find out what will be the oxidation state of phosphorus, and because if oxidation state is lesser than +5, there must be presence of pH bond or PP bond, that we know. So that information also will be helpful to find out whether pH bond present or not. But it is better if you can remember the structure. That is the best way. So I will suggest that practice the structure. That is, when formulas are given, you should draw the structure of the compound. So these are the 4 compounds, that is H4P2O5, O6, then H3PO3, H3PO2. Now in this case we have 2 pH bond, that is for this one. But the question is the pair that contains 2 pH bond in each of the oxoacids. So it is not that one oxoacid there is presence of pH bond, another oxoacid there is no pH bond. So that will not be the correct option. Both should have pH bond. Okay. And here we have only PP bond. Then 1 pH bond. So this is also not correct. This one is fine. This one is fine. So basically here H3PO2 and H4P2O5. If these 2 compounds are present together, that will be the correct option. Okay. H4P2O5 and H3PO2. So can you tell me which option will be correct where both these molecules are present? That is H4P2O5 and H3PO2. These 2 oxoacids are present in which option? Four options are there. H4P2O5 and H3PO2. So this is the correct option. Okay. Because if you consider first option, then here we have, but this one we do not have any pH bond. So that is, it is not correct option. Then here we have, but here we do not have. Then H4P2O5, this is containing pH, but there is no pH. But only in option 2, both the compounds are having pH bond, that is 2 pH bond. Fine. Good reducing nature of H3PO2. This is attributed to presence of how many POH bond or pH bond. Option 1 and option 4, there is mention of POH bond, and option 2 and option 3, there is mention of pH bond. But reducing nature, when we are talking about this property, it is because of pH bond. So reducing nature, it is related to pH bond. So there must be presence of pH bond. So you cannot choose these 2 options as correct because it has nothing to do with POH bond. It has to be pH bond. Now the next question is it containing 2 pH bond or only 1 pH? The structure of H3PO2 you can see here. Here we have 2 pH. So that is, it is very good reducing agent. H3PO3, that is also has some reducing property, but as here number of pH bonds are high, so that is why it will have higher reducing capacity, and 2 pH bonds are there. So that is why this is the correct option. Okay. Any doubt in these 2 problems? There is 2 lists, list 1, list 2. In list 1, what we have? Name of oxoacid. In list 2, we have oxidation state of phosphorus. So we have to match it, and accordingly we have to choose the correct option. Now see, here we have total 4 oxoacid, but in list 2, you have total 5 oxidation state. That is, 1 oxidation state there is extra mentioned. Hypophosphorus acid, orthophosphorus acid, hypophosphoric, and orthophosphorus. Now remember this "ik" or "as", it has some significance because when it is "as", it is actually related to the lower oxidation state. So hypophosphorus and hypophosphoric, these 2, if you consider, then obviously the name where it is "ik", that will be having the higher oxidation state. Similarly, if you consider orthophosphoric and orthophosphorus, "ik" will be having the higher oxidation state. Just remember, in case of Fe2+ and Fe3+, What we say? It is ferrous, it is ferric. That means whenever there is ick, that is related to the highest oxidation state. Hypophosphorus acid, that is H3PO2. Here oxidation state you can easily find out, but formulas are not given, so you have to remember the formulas. And for 3 hydrogen it is 3 into 1. For X it is that is phosphorus, it is X because that is the unknown value we are trying to find out. And for 2 oxygen it is minus 2 into 2. Overall charge is 0 because it is neutral molecule. So from this you can understand X value will be plus 1. So A is related to 5. Now A related to 5, that you can find in option 1 and option 4. So you can easily cancel out the second and third option. Then orthophosphoric acid. It is H3PO4. Similar type of calculation we are doing. 3 hydrogen, 4 oxygen. Overall charge is 0. So from this you can get it is plus 5. That means B is related to 1. Now B related to 1, we have already cancelled out these two. But B related to 1, that you can find only in option. So see, just 2 compounds you have done the calculation and you can reach the correct option just by eliminating. And if you follow this way, you can also save your time. So you don't have to consider the other compounds. But here we will see all the compounds. Hypophosphoric acid. So if it is us and plus 1, so it must be greater than that. So now it is plus 4. Similar calculations we have done. 4 hydrogen, 2 phosphorus, so that is it is 2 into X, and 6 oxygen, it is plus 4. That means C is related to 2. So C related to 2, option 1, and the last one it is plus 3. That means D is related to 3. Okay, this will be the correct. But remember, just if you are seeing that by eliminating you have already reached the correct option, then don't waste your time by doing the full calculation. Fine. Any doubt? Is it clear?
Yes, ma'am.
Here one oxidation state, that is 1, 2, 3, 4, 5. 2 oxidation state. This is actually extra that is mentioned. Now we will start another next group, that is group 16, which is also known as oxygen family, because based on the first element we call each group as that is family, that is oxygen family. In case of group 15 we say nitrogen family, like this. So first we have to consider what is their metallic nature or non-metallic nature. Now see, the first 3 elements, they are actually non-metal, which is clear from the color. Then tellurium, it is in between polonium and these 3. So it is metalloid, that is having property in between metal and non-metal. And the next element down the group, metallic nature increasing, so it is metal. But mostly this last element, livermorium, we do not consider it much, and you will hardly see any reaction of this element because this is radioactive and this is from 7th period. Okay, so mostly the discussion that you will see in this group, that will be up to tellurium, because polonium also it is not very, its occurrence is not very high. Fine. The initial 4 elements, that means O, S, Se and Te, you can call them together chalcogens. Now why we have this type of name? Because these are ore forming elements. What is ore? That we know. And on the grounds that are extensive number of metal ores are found in the earth crust, that is natural presence, in the form of sulfide and oxide. Now sulfide and oxide is H2 minus and O2 minus. That means these 2 compounds, these 2 elements basically, they are present as anion in the ores, and these ores are naturally found. So in the ore, as they are present in the form of anion, so that is why they are called chalcogens. Oxygen is the most plenty accessible element in nature. See, it is around 20% of air by volume. And if we consider world's mass in the form of silicate, because in silicate there is presence of oxygen, in carbonate there is presence of oxygen, oxide is obviously oxygen, and in sulfate also there is oxygen. So if you consider these anions which is also containing oxygen atom, then it is 46.6% of the world mass. But most of the oxygen in the air that is produced from photosynthesis by plants, and it has another allotrope, that is another physical form is possible, which is ozone, though O2 is the most common form. Now as it is, its occurrence is very high, which you can see from the value abundance in earth crust in ppm unit. So oxygen, its value is maximum 10 to the power 5. After that it is sulfur 10 to the power 2, but as you are moving down the value is decreasing. See, now the power of 10 is 2. So these two are their occurrence comparatively lesser, it is compared to oxygen and sulfur, and polonium is further less, it is -3. So down the group occurrence is decreasing, and oxygen is the most, its occurrence is maximum. The second element, that is sulfur, it is 16th most inexhaustible element. In its combined state, that is when it is not in free state, it is not simply sulfur, it is present in some compound, that is combined state. It is also found in ores, that we have already mentioned in the first point, that is present as sulfide anion. You can also find sulfur in many organic substances like mustard eggs, seeds, onion, wool, garlic hair. So see, in some cases, that is garlic, eggs, onion, there is some specific smell, and that is actually because of this sulfur. Then selenium and tellurium, these are also found as selenide. So selenide is analog of sulfide or oxide. That means now it will be like this, that is AC containing 2 negative charge. Telluride means it will be containing 2 negative charge, that is analog of oxide. So these two are also found as metal selenide and telluride, where these are basically present as anion. That is also possible. Next, polonium. This is also radioactive element, though it is here from color it is present as metal, but it has also radioactivity properties. Okay. Now both the color we cannot mention together, so that is here only blue color, which signifies the metallic nature, that is mentioned. So this is the decay product of thorium and uranium. This is also radioactive, and the last one is obviously synthetic. It is not natural, it is synthetic, as well as it is radioactive. Livermorium, in short, LV. Okay. Electronic configuration. Here we have atomic number as we are moving down. It is 8, 16, 34, 52, 84, 116. Now for each group, it is not just for group 16. Even if you consider any other group like group 15, or after this there will be group 17. One thing is common, that is if I am writing all these numbers, there is an easy way by which you can remember the atomic number. So what you have to do is just remember the atomic number of the first element, and when you are moving towards the second, just add 8. Then from 16 to 34, just add 18. 34 to 15, add 18. 52 to 84, now you have to add 32. So these numbers are actually common. Even if you consider nitrogen, that is group 50. So atomic number is 7. Then next element is phosphorus. What you will do? 7 plus 8. Now it is 15. Next element, nitrogen, phosphorus, arsenic. Now what you will do? Again add 80. So in this way, you can easily find out what will be the atomic number of all the elements down the group. Just follow these numbers and you have to add it. That is from second period to third period, when you are moving, add 8. Third period to fourth period, add 18. Then again 18, then again 32. Now the number is different, 32. Now look at the electronic configuration. After helium, that is the configuration of 1s2, there is 2s2 2p4. So here principal quantum number is 2, and that is n value is 2. So it is from second period, then n value is 3. So this part is common, that is 2s2 2p4, 3s2 3p4, 4s2 4p4. And in general, how you can write it? n is 2 np4. So total number of valence electron 2 plus 4 6, which is the last digit of group 16, right? In this way you can remember it. Now when you are moving from third period to fourth period, what is the difference? Here you are having 10 electron extra. So that is the reason when we move from third period to that is 16 to 34, you are adding 18. That means 10 electron extra compared to 8. And that is because of this 10d electron. So now you have presence of 3d electron. When you are moving from fourth period to fifth period, from selenium to tellurium, now also you have 10d electrons. So basically what I'm trying to say, in case of oxygen and sulfur, there is no d electron. But in case of selenium, tellurium, and also polonium and livermorium, there is presence of d electron. So when it is principal quantum number 4, then it will be n minus 1, that is 4 minus 1. When it is 5, it is n minus 1, that means 5 minus 1, which is 4. And now when you are reaching group period 6 and 7, what is the difference? Now you also have 14 electrons. So that is the reason the difference you see here, further plus 14. And this is because of 14 F electrons. Okay. If it is asked that in which case there is presence of both F and D electron, the answer is it is polonium, and this we actually do not consider, though it is mentioned here, but mostly the discussion will be restricted up to this point because this is synthetic. So F electrons are present in the last element polonium and D electrons present in case of selenium tellurium. But oxygen sulfur, there is no D electron. But remember, in case of oxygen, there is no D orbital because it is from second period. But sulfur, though there is no D electrons, but vacant 3D present. Try to understand the difference. Here you do not have D electron, but that doesn't mean 3D is not present. 3D is present, but it is vacant. But in case of oxygen, even you do not have vacant 3D because it is from second period and there is no 2D, right? So in this way, you can remember the electronic configuration, and general electronic configuration is NH2NP4. Is there any doubt?
No, ma'am.
Now we will see different atomic properties. First atomic property is how atomic and ionic radii is changing down the group. So down the group, oxygen, sulfur, selenium, tellurium, polonium. In the y-axis, we have the values of atomic or ionic radii in picometer unit. Okay. Now down the group, as we know, extra valence shell is added, so obviously size will increase. That is common for any group. But one thing which is noticeable, when you are moving from oxygen to sulfur, the difference is around 80 minus 40, that means around 40 picometer. But when you are moving from sulfur to selenium, now the difference is only 20. The next difference, that is also not very high. So I'm trying to say only the first two elements there is bigger difference. Now what is the difference? Why it is so? Again the same reason. When you are moving from oxygen to sulfur, there is no presence of D electron. So there is increase in the value of atomic radii, and it is only because of this extra valence shell addition. But when you are moving from sulfur to selenium or selenium to tellurium, there is also extra valence shell added. But now you have addition of 3D electron also. And we know D electrons, not 3D only, 3D, 4D. D electrons are having poor screening property. That means the positive charge of nucleus for the outermost electron, because of poor screening property, this attraction will be very high. As a result, the size of the atom or ion, that will reduce. Okay, so this is the opposing effect. But this is the effect for which size should decrease. But there is another opposing effect, that is extra valence shell addition, for which size should increase. Now the combined effect of these two opposing facts, if we consider, Then there is the valence shell addition. That factor is winning over this. So that is why there is increase. But the increase is not very high. Unlike the increase when you are moving from oxygen to sulfur. Okay. Ionization enthalpy. It decreases down the group, that we know, because of increasing size. So you can easily remove the outermost electron because it is in the distance between the nucleus and the outermost electron, which is increasing. So you can easily remove the most loosely held electron. But if you have, if you look at the values, see, down the group there is increase, that is fine. But again the same thing. When you are moving from oxygen to sulfur, there is difference of around 1400, 1000. So this 1200 minus around this value 900. So difference is very high. But the next, there is decrease, but again the difference is not very high. Again the same reason. The reason is because of the poor screening property of T. So the decrease that you expect, the decrease is not so high, rather than it is comparatively lesser, and it is because of this poor screening property of d orbital. So that is why the attraction of nucleus and electron, as it is high, it will be difficult to remove the electron. So the value is decreasing, but not much. If we compare the ionization enthalpy values of group 16 elements with that of group 15 elements, they have lower ionization enthalpy values compared to those of group 15 elements in the corresponding period. That is, when you are considering same period, suppose if you are considering second period, then you have nitrogen from group 15 and oxygen from group 16. Similarly, if you are considering third period, you have phosphorus and then sulfur. Now when it is, that is just fix the period, then if you are comparing the ionization enthalpy, then it is lower. Now why it is so? Because in case of group 15, the configuration is NH2NP3. So this is half field stable configuration, and to break this configuration it is a difficult process. But in case of group 16, it is NP4. That means one electron, if you are removing, you are reaching stable half field configuration, which is facile process. So that is the reason they have lower ionization enthalpy. But remember, you cannot compare nitrogen with sulfur because it is down the group as well as period is increasing. So two factors are there. So that is why you cannot compare. If you are comparing, you have to do it in the same period. So that is, it is mentioned in the corresponding period. That is same period, then only you can compare. And melting point, boiling point, though it is not atomic property, it is actually physical property. But see, we know that down the group, melting point, boiling point always increases because of increase in mass. So van der Waals interaction also increases. So see, melting point in degree centigrade unit, it is increasing. Boiling point also, only the first one is negative. So see, it is negative. That means what? It is gaseous in nature. That is, under normal condition, oxygen, how it exists? It exists as gaseous. That means its boiling point, it will be very, very low. It is having negative value. But sulfur, it is solid. So that is why now it is positive. Okay. Some more atomic properties are left that will be also discussed in the next class. So regarding all the slides in this class, you have any doubt, please tell me. So if you do not have any doubt, we will end the session here. Thank you for listening.